So we arrive at the final part of our course, and here we will discuss about the nonlinear systems. So here also, done in the discrete time systems, we will be actually giving some brief idea about nonlinear systems uh, and some analysis around nonlinear systems, how to study them, and on these details. So this will be very brief, and actually there is a total entire elective course for you on nonlinear systems. So if you get interested, you can have that course in your, I think, in your final year. But now you will get an overview of how to deal with nonlinear systems, what are the different properties, etc. So that even if you are not taking that elective course, even then you are having some idea about nonlinear systems, and you are able to handle them if required in your future life. So let us see how the nonlinear system looks, and it is basically there is no definite structure like the linear systems had, which is the ABCD matrices, because here it can be any function. The x dot, the dynamics can be basically any function. So if the function is of the type if that function is of the type ax, where a is a constant coefficient and x is the variable with degree 1, so here the degree is 1, so then it is a linear function. So this is linear function. However, you can of course understand, if we generalize this thing, then the power of x can be any alpha, which it may not be necessarily 1, any real alpha it can have the power. Then a, it can be a function of time or some other variables, also some argument t, so it can keep on changing, and this can have some index power which is not equals to 1, and these constitute the nonlinear phenomenon. And this actually not necessarily also that this has to be a polynomial degree type of term, it can be any other different term also, something which is not like this. Anything which is not like this is basically nonlinear. So this ftxu can be such a nonlinear function, and that will comprise the nonlinear dynamics. Why htxu? This can also be a nonlinear function. However, this is not a botheration, because this is simply an algebraic relationship. So if you know what your x, t and u are, you can directly calculate y. However, this is what is interesting for us, because it creates an entire range of very rich and diverse dynamical systems with very typical phenomenon which is absent in linear systems. So what are those typical phenomenon? These are some of the very well observed phenomenon, nonlinear phenomenon, which are absent in linear systems are listed here, and let us go through this phenomenon one by one, and just we will get a glimpse of what these are. We will not dive down very deep, just have an overview of this phenomenon. So what is the finite time phenomenon? There is this finite time phenomenon, which is basically either the system goes to stability or instability in finite time. So in linear systems we have observed that we can have asymptotic stability or instability. However, in nonlinear systems, in a certain class of nonlinear systems, we can observe finite time behavior also. So we take an example, a very simple example of scalar systems. Here in the finite escape time, you can observe this is the nonlinearity, which is this is a simple scalar system. So you can very quickly do an integration and find out the solution which is expressed here. And if you have actually if you have your x0 as negative, then when t is tending to it should be 1 by mod x0, t is tending to that 1 by mod x0, then your xt will become infinity. So you don't need to wait for time going to infinity to have your system escape. So why it is called escape? It is escaping actually the state space as if, so it is escaping to infinity. So here if you draw the response, basically this being your xt, maybe this is t, you are starting from some negative value. So let us start from here, x is negative. So as t increases, you are approaching infinity, and basically you are approaching minus infinity here, because it will have a negative sign. So it is like this, you are going out. So to go to infinity, you are basically going to infinity in some finite time. So this is the finite escape time. There can be many other, so this is not the only dynamics which is giving you finite escape time. There can be many other such dynamics. Finite reaching time, this is a typical dynamics of a finite reaching time. In general, if you find dynamics like this, where alpha is in 0 to 1, this will have finite reaching time. You can actually solve for a general alpha in 0 and 1, 0 to 1. You can integrate and you will find out that it happens like that. So for alpha equals to half, this is the solution, and you can see very straightforwardly that xt will be 0 when t is this much, and when xt becomes 0, after that your x dot also becomes 0. So you actually reach an equilibrium point. So after that you do not your system does not evolve further. So your response is like this here, that x0 is greater than 0. So you something like this, you reach 0 at this point time, which is this 2x0 to the power half, like this. So I hope the integrations are correct. So please check for yourself whether the solutions which I have found out doing integration are correct or not. But I hope these are correct and you get the idea what we are trying to highlight here. So this sort of phenomenon can appear due to the various sorts of nonlinearities which could be introduced to a system. Next comes the jump phenomenon. In jump phenomenon, basically this sort of a phenomenon happens in case of springs or systems which has spring like behavior. So normally what happens in spring, we model the restoring force as proportional to the displacement about its mean position. So that is the linear spring. However, in general you also have a cubic term actually. So that contributes to the restoring force in case the displacement becomes larger, and if your K2, the coefficient of this cubic term is greater than 0, it is called a hard spring. If it is less than 0, it is a soft spring. Obviously, if it is equal to 0, it is the linear spring, because this term then vanishes away. So what happens here actually in this sort of systems, if you try to plot the amplitude frequency plot, so the frequency response basically, so what you will get, you will not get a curve. Naturally, normally the linear one will have some smooth curve like this, and the peculiarity will be that for none of the frequencies you will have more than one amplitude, and it will be a continuous curve. The amplitudes will be continuous, amplitude frequency plot will be a continuous curve, and at no frequency there will be two amplitudes, so there is no ambiguity. However, in this sort of systems, if you plot the frequency plot, then what you will see that it is going, so suppose I start from this point 1, it will go 1 2 7 3, so it will go like this 7 3, and then there is a sharp jump to 4. It is not continuous, it is not going through 3 6 and then 4. From 3 it is directly jumping to 4, so there is a discrete jump, so there is a discontinuity. And then it goes to 5, and then if you trace it back, then from 5 to 4 it goes, but it does not go to 3 back, it goes to 6, and then it jumps again to 7, and then to 2, and then to 1. So there is this region is there, which is a sort of a unstable, you can say. It exhibits some sort of an instability, so the system does not really stay at this region. So so this is the way. So this is one for hard spring, you can see, another for soft spring, you can see. Here also you have this jump from 3 to 4, then you go to 5, and when you come back 5 to 4, then to 6, so you don't go from 4 to 3, you go to 6, and then from 6 to 7 you go, and then again come back. So this is the jump phenomenon. Then you have a typical pendulum system exhibits the typical behavior of multiple equilibrium points. So multiple equilibrium points we have touched upon in our discussion in linear systems also, that we told that in nonlinear systems there may be multiple equilibrium points. So this is a very standard system which exhibits multiple equilibrium points. However, please note that almost all nonlinear systems will exhibit multiple equilibrium points. This is a very standard example and very easy to understand. That's why we are introducing this here in this lecture. So the dynamics in the tangential direction is this, and if you choose your states as the angular as the angular position and the angular velocity, so then your state space representation is like this. And if you try to solve the equilibrium points by making x1 dot equals to 0 and x2 dot equals to 0, you straight away see that x2 is 0, and then sin x1 has to be 0, and that gives you solution of x1 as n pi. So any n, positive or negative, will give you an equilibrium point. So you see so many equilibrium points are there. So if you basically look at the state space, so this is x1 and this is x2. x2 is 0, so this is the equilibrium point. x2 0, x1 is also 0 here, so if n is 0, so this is of course an equilibrium point, the origin. However, there are so many other equilibrium points here. All of these points are having x2 equals to 0, and x1 is changing. This is plus 1 pi, so this is 0, this is pi, this is 2 pi, this is 3 pi, like this. Here it is minus pi, minus 2 pi, minus 3 pi, like this. So you have so many multiple equilibrium points you are having. So so this is the phenomenon of multiple equilibrium points. Yeah, however, one thing we need to note, let us try to see the system physically. Where are these equilibrium points? Basically, if you see, one equilibrium point is this one, when the blob is here, pendulum mass is here. So this is the point corresponding to theta equals to 0, theta dot is also 0. So theta dot is the x2, right? So at any equilibrium point x2 has to be 0, and this is one equilibrium point where x1 is also 0, and we know that this equilibrium point is a stable one, because if you move the pendulum a bit away from this equilibrium point, it will again come back to here naturally. So this is a stable equilibrium point. What is the equilibrium point which is pi 0? So pi 0 is this equilibrium point, which is vertically upwards. So excuse my drawing, so this is not a straight line anyway. So you understand that we have the vertically up equilibrium point. Here also your theta dot, which is x2, would be 0, and your theta is basically pi here. Theta is pi here. So if you go in a positive direction, so you reach this position where the angle would be pi, and this is also an equilibrium. However, this equilibrium is unstable, because we know that the system by itself cannot stay at this position. Very minute perturbations on the system will make it go away from this equilibrium point. So this is not a stable, this is an unstable equilibrium point basically. And then now if you look at the other equilibrium points, which are 2 pi, 3 pi and all, so 2 pi is basically again this lower equilibrium point, 3 pi is this upper equilibrium point. So all the other equilibrium points are basically repetitions of the same two equilibrium points. So in a way, what happens here, the mathematical system is having so many multiple equilibrium points, infinite number so as to say, but the physical system is having only two equilibrium points. The actual system is only having two equilibrium points. The mathematical system, the mathematical description is actually superimposing the repetition of the equilibrium points on the same two equilibrium points. So this sort of situation can also arise, and that is why the pendulum system is very peculiar in nature. Next we see the van der Pol equation. This is also a very typical nonlinear system. Here what happens, you see that this equation is almost like a equation of motion. So it is a motion dynamics. You have the acceleration x double dot, you have the velocity x dot, you have the position x. Now you notice that with the x dot there is a nonlinear term, and normally with x dot the coefficient that we have, which is called the damping coefficient. So this one we also term as the nonlinear damping, and the strength of the damping is decided by the scalar parameter u. So u decides the strength of the damping, and the nonlinear term is known as the nonlinear damping. The phenomenon, the unique phenomenon which is exhibited by van der Pol equation and exhibited by many other systems, but it is often studied with the help of van der Pol equation, is the limit cycle behavior. So the limit cycle behavior will be exhibited for all u greater than 0. So let us we will look into the limit cycle, what is the limit cycle, but just before that let us just categorize this equation in these three parts. If you have this nonlinear damping 0, then the equation basically reduces to a simple harmonic motion, and it will be a sinusoid. The response will be a sinusoid, and if you look at the state space trajectory, there will be circles will be there. So that is known to us. Now if you have this as greater than 0, then the damping will be positive and the system will experience damped oscillations, and if it is negative, then it will experience negative damping, which is equivalent to pumping. So what is happening in damped oscillations means your oscillations will die down. As we know, in second order system response, we know that we have oscillations, but that they die down in time. However, in pumping, the oscillations will increase with time. So that is the thing. So now we look into what we call as limit cycles. So here you see we have plotted the trajectories of the system with some values of u. Here u is 0.001, which is very close to 0. That means you are getting almost circles, right? You can see that trajectories are almost circles. Here u equals to 0.2, you see that it is not exactly a circle anymore, and also you start noticing a behavior which is not so much apparent in the first plot, though it is present in the first plot. The behavior is this, that the trajectories surrounding this closed curve which is in the middle, the trajectories around that closed curve are actually converging to that closed curve. This is the phenomenon of limit cycles. Limit cycle is basically a closed trajectory or a closed curve, you can say, in this phase plot or in the state space. So where all trajectories either converge to or diverge from. So this is the simple way you can understand what is the limit cycle. So this is a limit cycle. This is limit cycle. So here you can typically observe this behavior. This limit cycle is stable because all the other trajectories are converging to this limit cycle. If the trajectories diverge from the limit cycle, it is called unstable limit cycle. In the first plot also you will notice that there are lots of trajectories which are actually converging to some closed curve inside here. So these are very close together, so you are not able to appreciate properly. But as you increase you will see that the closed curve, which is a limit cycle, becomes very typical in nature. It changes also its shape, and trajectories surrounding it are actually converging to it. So you can take different initial conditions and observe these trajectories. This is a response for u equals to 0.2, which is quite close to 0. You can see that the response is quite similar to the harmonic motion, which is a sinusoidal motion. However, it is not exactly sinusoid because u has some value, and as you keep on increasing u, you can observe that it is very different from sinusoid, but however it is a periodic motion. So the limit cycle behavior guarantees a periodic motion. So if there is a limit cycle, that means the system is coming back to the same point again and again along that trajectory. So the limit cycle is basically a trajectory in the state space. So the system is moving in that trajectory again and again. So that means that there is a periodic response of the system coming out. Some other phenomenon. So here, as we observe that there is a periodic motion, and you can see that it might so happen that there are a lot of frequencies in this periodic motion. So here basically a class of systems can have this sort of a phenomenon where if excited by a single sinusoidal input, if you excite by a single sinusoidal input frequency, the system response can consist of subharmonic, harmonic, or even almost periodic oscillations. So they may not be exactly periodic. So all this can combine together and form the response of the system. Chaos is a very typical response. It is highly, this sort of systems are highly sensitive to the initial conditions and other external conditions. So it is so sensitive that a very minute shift in the system initial conditions or this external environment gives an entirely different response, and it is such that it appears that the system behavior is almost random and unpredictable. However, it is not so. It is governed by a very definite set of nonlinear dynamics. However, the dynamics is such that a very small, very minute perturbation will give rise to a totally different system response. These are chaotic systems. We look at some common nonlinearities just to appreciate that how common they are. Actually, the nonlinearities are basically very common to practical systems. They are there in the systems. So a very common nonlinearity is a relay nonlinearity. There are lots of switches and relays in any system. So what is the relay nonlinearity? You can see that the relay or the switch behaves as an on-off sort of a behavior is exhibited. So when the input is like greater than 0, the output is something, and when the input is less than 0, the output is exactly the opposite. So it is like an on and off situation, so very binary in nature. And some more the richness of the relay can, the nonlinearity in the relay can be richer if we consider that there is a dead zone sort of an phenomenon in the relay. So you are giving an input, but the relay is not operating, and there may be some hysteresis present also in the relay, as you can see from plot B. Saturation is a phenomenon where you could be having a linear system, but it saturates somewhere after going beyond a certain point at the in the input. So the output basically saturates, so the output does not grow any further, and this this line between the two saturation limits could be linear, it could also be non-linear also, but normally when we talk of saturation we visualize it as a linear curve, and actually the curve is smoother. There is no sharp edge here like what we see, like this sharp edge. The sharp point is not there. Normally it is a smoother one. However, we sometimes approximate with the sharper approximation. Dead zone, you can see what is the dead zone. Already explained that the input is there but the output is not coming out, so this is the dead zone. Then this is very observable phenomenon, very likely thing which we observe in many systems. Quantization, when we quantize a signal, then we are actually introducing a nonlinearity, because with the input level changing we are not changing the output level. So we are basically introducing nonlinearity here. So these are very common nonlinearities. There are other nonlinearities like this. Hysteresis, we know this magnetic property of magnets, there is hysteresis like this. Then backlash is a property which happens at the gears basically. So in mechanical gears, so the input and output speed is having a non-linear relationship. They are not exactly linear. We expect that the input shaft speed and the output shaft speed would be in tandem with each other, but it is not so. So when we increase the speed and when we decrease the speed, it follows two different curves, and this is we actually did some experiment on motors and etc., and we experienced this sort of phenomenon in the system. So there is a lot of nonlinearity in any practical system. There is a lot of nonlinearity, and hence actually we are always dealing with nonlinear systems. However, there is no single mathematical tool like the Laplace or the Z transform with which a wide variety of nonlinear systems could be analyzed. So what happens basically, we actually categorize the nonlinear systems. So if this is a set of nonlinear systems, we categorize the nonlinear systems as per their typical behaviors and study these classes of nonlinear systems. Suppose this is having some behavior B1, B2, then B3 like this. So we study the behavior B1, and any system exhibiting that behavior B1 then gets studied. However, the study of the system with behavior B1 will not have anything common with the study of system of behavior B2. So the actual analysis steps and approach may be completely different. So there is no single approach and mathematical tool which could be utilized all through B1 to B5 or all through all the phenomena. Every phenomenon has to be looked differently. So that is the complexity that nonlinear systems introduces. However, that is also the richness and the beauty of it. Now one who is adept in the maths and the mathematics, one who likes doing mathematical analysis will find it beautiful. However, for normal people and engineers, this is not a very useful situation. This is not a helping situation actually, because there is no general approach that is existing, uh, and we cannot actually fix any general performance and design criteria. What are general performance and design criteria? Like performance criteria, we have this percentage MP and this TR, TS, so rising time, settling time. So these are very we cannot actually define these things anymore for nonlinear system responses. And design criteria like your phi m, am, these things. So this is phase margin, gain margin. These are the very definite design criteria for linear systems. However, there is no definition of these things in these things cannot be defined even for nonlinear systems. So what would be the design criteria? This is very open situation actually in nonlinear systems. So what do we generally do as engineers and as even mathematicians? They generally resort first to something called linearization. So we try to linearize the system about some operating point actually. So what we do is basically we can always, if we have a non-linear function like this, we can visualize this as pieces of linear function. So this is a very standard approach. We visualize it as pieces of linear function, and if we are interested in operation around a particular region, suppose this region, then we linearize the system about this region. Supposing this is the midpoint taken, and we linearize it. So beyond this region, in this region the linearization would work. It would be giving same behavior as the nonlinear system would give in this same region. However, if we change the region, to this one or even the next region, the same linearization will not work. In that case, what we do, we do piecewise linearization. Piecewise we linear, so we take different operating points and we linearize, and then we can analyze the system also. However, this approach is quite tedious in nature. One reference point linearization is good, but if you have to linearize for all these points, then it is basically a very difficult problem we are trying to solve. What are the other well-known methods? Other well-known methods are very useful phase portrait analysis, which we actually saw in the van der Pol problem, van der Pol system. We saw the phase portrait analysis. Then we saw the phase portrait actually. We'll understand what exactly is a phase portrait and how to draw it, and there is some analysis in phase portrait also. With phase portrait we can do. Then there is the describing function method and Lyapunov analysis, perturbation method, etc., etc. We will study the describing method and Lyapunov analysis as well in this course. So these are very standard techniques. We will just touch them briefly. They are having some more details also, but we will not dive so much deep into each of the techniques. We will just give you an idea of what these are, so that you can work with them, or if you needed you can start with them and start to go deep down if required. So with that we come to the end of the lecture, and I hope you had some interest in nonlinear systems, and with that I would like to end the lecture, and thanks you for your attention.